All right, so today we're going to continue with our differential equations, this time looking at some applications, but before we get there, we're going to deal with C, ln and C. So what happens to C when we are taking a natural log? Because there are good ways of utilising it and not so good ways. So okay, so that is a pretty easy question. We know that when we integrate this, we get ln of x plus c. Now, in differential equations, when we are trying to find c, it's actually easier if the c is part of the absolute value, the grouping that's being natural log. So we use our log rules, and we change this to this. Doesn't matter what the letter is. That k is not the same as that c, but it still is just a number, all right? We haven't changed it at all, but using our log rules of this, we can put this together as this, all right? And that means that when we are given a piece of information, say when like this, that when we're actually trying to solve this, that we would get 3 equals ln of kx, k full stop, times 1, and we take our natural logs, then we can find it easily because we don't have to worry about that e to the power of. So that's just a little bit about finding that constant. Okay, so applications. The reason, I don't know whether it's the reason actually, but one of the reasons that this exists is to actually help us to model real life situations. So in a lot of scientific fields and business worlds, there are equations that are exponential in growth or in decay. All right, so population growth, you hear it talked about. You have talked about, I mean, the big one now is carbon credits, carbon stuff. All right, you've got the economy growth, you've got COVID growth. All of those things, when they were talking about it way back in 2020, when they started putting all the graphs on the television and stuff, and you saw it, and they started squashing the graph up so they could actually fit the next value on, right? It started off nice, you've got 1, 2, and 10, and suddenly we had 100. So boom, they squashed the graph up and stuck 100 and everything went a little over here. Then the next minute, there's thousands of people with it dying or whatever it was, and they squashed the graph up again so that they could fit that 1,000 on. So they kept squashing the graph up, and that's where logs and exponentials, that mapping of those sort of things, became helpful because we could squash the graph up and deal with them in that exponential rate. Okay, so the things that come up are things like population growth and decay, and that can include things like viruses. All right, it doesn't have to be just that. So we can have viruses, we can have radioactivity. Obviously, in the times of nuclear and radio destruction, we want to know how long it takes for it to disperse. That is an exponential sort of thing. We can have it in that inflation or business type of setting. So whatever it particularly is, we get a differential equation that looks like this. The rate of change for whatever we're interested in is proportional to something happening. All right? So that particular differential equation becomes huge. This particular differential equation has a solution of this. All right? Now, what we actually, I don't need that plus C actually because we've put the A there. What we've actually got here is a relationship between a differential equation, something mapping something in the real world, and its solution set. The issue here is that in this paper, we are being tested on integration. And if we just start there and solve it, we have not integrated. So stupidly, you're not allowed to just know this. You have to show it, all right? So you actually have to prove that that equals that. It's really easy, but in this particular instance, if we had dy by dt, because usually it's over time in all of these things, equals kx. ky. Then, when we integrate this, right, we need to separate the variables. So we're going to get the integral of dy over y and the integral of k dt. So this is the part that you have to be able to show to be able to get that integration tick, to be able to get excellence for solving it. Okay, so when we solve this, we've got 1 over y dy, and we've got k with no t's, but t is going to appear, okay, which then gives us ln of y equals k plus c. Then we come into this part. So this bit here, we're going to actually put up here, but we're going to change that plus c, and we're allowed to do it just straight away, and put it as y equals e to the, we forgot the t, e to the kt, and we've got this one as well, but remember that we can just write this as e to the a e to the kt. Right? So that little bit there, we have to be able to parrot. We have to be able to do that at the beginning of our question, and then we deal with this. All right? So here's a question. Okay, I'm going to copy it off the book. The half-life of 42K, which apparently is some radioactive isotope of potassium, right, is 12.45 hours. The DE modelling this they may or may not give this to you. If they give it to you, it's probably downgraded to a merit. So you have to kind of know that it is dn over dt equals negative kn. Now, why negative k? Because it's going down. So sometimes it's easier, you can have a k. Just when you find it, it'll be a negative number. You can have a negative k, and when you find it, it will be the positive number. So it's just a little bit of understanding of that particular thing. So, where n is the number of atoms present at time t. What percentage of isotopes remain after 10 hours? Okay, so one of the things you need to realise is in this equation, A will always be your initial value, all right? Because when time equals 0, this little bit of the expression equals 1. So therefore, this will always be your initial value. You don't have to find that one. They will quite often say to you, the population started at 32,000. And you then know that that's A. You don't have to go through the process of showing that's A with t equals 0 or anything like that. Okay? So t is the time we're taking, k is what we're trying to find so that we can use it in some sort of instance. So we've got this differential equation, and the first thing we want to do is show that we can get from there to here. So dn by dt equals negative kn. dn over n equals negative k dt. Integrating both sides, ln of n equals negative kt plus c. N equals a e to the negative kt. All right, so that's just completely parroting that little bit there to show the integration to allow us to have the marks. A few years ago, we used to just teach that we could do this, and then all our kids failed this excellence question because they, without telling us, decided that they needed to show this for you to be able to get it. So, lesson learnt, now we all show it. All right, so we do read the markers reports in order to make sure that we're doing the right things with you. So, a half-life occurs when? Halfway through. All right, so it's a 0.5, isn't it? So when t equals 12.45, we've worked out here that it's in hours. All right, so checking that our two unit measurements are in the same unit. Sometimes they do change between minutes and seconds on you, and you need to be aware of that and make sure you look carefully for it. Just little tricks along the way. Don't know why they need to trick you, but they do. So when t equals 12.5, n is going to equal 0.5 of A, the half-life. All right, so the half-life of A is going to be that. This is absolutely gone off the screen, and I thought I'd pulled everything. Thank you. No, that one. I can pull it down, please. Thank you, Alex. All right, so if that is the case, then when we go back to this equation here, all right, we've basically sorted it all out. So we've got A being this, so A is equal to 0.5n, and we're trying to, and T is 12.45 for here. So what we've actually got left with is just that relationship we are looking for. So we've got n equals 0.5. That's not what we've got. We've got when t equals that, A will equal 0.5 of A. N will equal 0.5 of A. Okay, so 0.5 of A equals A e to the negative k times 12.45. All right, so we've substituted for that. We're going to cancel out the A's, getting rid of our initial, which we don't really need to know about at the moment, 12.45. We're going to solve this by taking logs. So negative 12.45k equals 0 ln of 0.5. And we're going to solve that in our calculator. So we're going to find ln of 0.5, and then we are going to divide that by negative da-di-da-di-da and get, hopefully, checking for me, that k equals 0.056. Yep. So that is just a multiplier. All right. That belongs in our equation here. All right. It's our proportional relationship. The relationship between the change and the original is negative 0.56. That's the relationship between them. Okay. So it's the rate of change as such, I suppose. Now we need to answer the question. So we've now got an equation that we can use. It is this one, n equals a e to the negative 0.056 t. All right. When n is the number of atoms present at time, what percentage of atoms remain after 10 hours? So we're after a percentage. Have we got A? Do we need A? No. All right, so we can go back to this equation here, where we've got this part here. All right, now all we have to do is put T in and find out the percentage that is left. Not 0.5, 10. All right, put 0.5 in, and we will be able to, put 10 in square. So after 10 hours, T equals 10, N will equal e to the power of negative 0.056 times 10, which is equal to 713? 12. All right, so that is what N is equal to, but the question here is what percentage of the isotopes. So this is not the number of isotopes. We're relating this to the percentage that we've got. So we had a half of them here. We solved this to find out what a half or 50% was. We're now at this percentage of it. So this is 57.12%. All right? So just got to make sure we answer it with what we're asking.